Hello, welcome to this class on solving problems on the topic of units and errors in measurement. I will begin by telling you the most famous cat and mouse story about uncertainties in physics. This story has to do with the experimental verification of this Einstein's theory of space-time curvature. We know that objects with mass are attracted by the gravitational field. Now imagine light coming from the distant stars. As it passes close to the sun, it can get deflected. This was what Einstein's theory was predicting, Einstein's general theory of relativity. Einstein's prediction set forth a series of attempts to verify this prediction. These experimental requirements were very stringent. For example, it's not possible to observe stars which are directly behind the sun. However, during an eclipse, you can make this observation. So, a first attempt was made during the World War I. A German expedition went to Crimea to take observations of the positions of stars in the sky directly behind the sun. This expedition returned home empty-handed because the conditions of the war did not permit them to perform these measurements. A second attempt was made in 1919. During this time, the experimentalists were much more prepared. They wanted to observe the positions of stars which are directly behind the sun by observing them during a solar eclipse. And then 6 months later, when the Earth went to the other side of the sun, they would compare the positions of the stars when the light did not graze past the sun. Was the position any different? Yes, they were expecting changes which were as small as 1 arc second, a very tiny displacement. Such a tiny displacement could also come from thermal expansions of the photographic plate on which they were trying to record this data. So they had to make sure that all their recording was perfect. In Newtonian theory, if a photon was a particle with a tiny mass, something which was non-zero, then it could perhaps have some gravitational interaction with the sun. It would get deflected by the sun, and therefore in Newtonian theory it was also possible to observe stellar deflection due to the gravitational field. The competing theory was that due to Einstein, where photon, despite being a massless particle, could be deflected by the space-time curvature. So let us look at how the experimental observations compared with the theoretical predictions. The Newtonian theory predicted a stellar deflection, that is, deflection of the light, assuming photons have a tiny mass. Due to the gravitational force of the sun, they predicted a small deflection of 0.87 arc seconds. Einstein's theory, which was grounded in a completely different framework, that of space-time curvature, predicted 1.74 arc seconds. And what did the experimentalists find in 1919? Eddington found the value to be 1.61 plus minus 0.40. This value of the uncertainty which they computed for their experiment was crucial in saying that Einstein's theory was right and Newton's theory was an approximation, it was incorrect. The error, the one standard deviation, is only 0.40, which is keeping the Einstein's value within the experimental measurement, but keeping the Newtonian value far away from the experimental measurement. So in today's class, we will look at some elementary problems related to uncertainties. Through this example, I have tried to show you the significance of uncertainties in physical measurements. I will begin with a very simple problem. and then slowly we will move on to more difficult problems. Most of the problems that I will discuss in this class today are on the topic of propagation of errors, but we will also do one problem on units in physics, physical quantities. Now let's look at question 1. The measurement of weight of sand was made by taking 3 successive portions. The result of these measurements were M1 is 25.0 plus minus 0.1 kg, M2 is 32.3 plus minus 0.2 kg, and M3 is 27.7 plus minus 0.1 kg. The question says, what is the uncertainty in the total mass? So here is a problem where we are doing 3 successive measurements, probably because we don't have a weighing balance which can measure the total mass. So I take the measurement in 3 goes, and in each go there is a certain uncertainty. Let's look at how we solve this problem. The total mass is the sum of M1 plus M2 plus M3. So the error in the total mass will be delta M1 plus delta M2 plus delta M3, or 0.4 kg, and we would report the total mass to be 85 plus minus 0.4 kg. Here in this very simple application we have used the propagation of errors, what one would do for the sum or difference of quantities. Note that it does not matter whether the error was on the positive side or the negative side. When we are reporting the error, we are assuming the worst case scenario so that the errors are not cancelling out in successive measurements. Therefore, we are taking the sum of 0.1 with 0.2 with 0.1. We are adding them. Let's look at a little more difficult problem. An object of mass 100 gram is dropped from a height of 10 meters. The time taken by the object to fall is measured with a stopwatch, and it is found to be 1.4 seconds. If the height is known with an uncertainty of 0.1 meter and the stop clock records with an uncertainty of 0.1 second, what is the value and the uncertainty in the acceleration due to gravity inferred from the experiment? When you drop an object from a height it falls, you can use the time of flight or the time of fall of that object to arrive at an estimate of the acceleration due to gravity. Let us find that to begin with. Here I drop a ball, the height is h, the time of travel is t, and from the relation h is equal to half gt square, I can compute the value of g. Plugging in the numbers, what do I get? I get g is 10.2 meter per second square. Now that's a little higher than the actual value of g. But then there are experimental uncertainties involved. So what one needs to see is whether your actual value lies within these experimental uncertainties. Let's look at the equation again. G is 2h upon t square. I can now use the propagation of errors for a product of quantities. For a product of quantities, we don't write the error as delta G equal to delta H plus delta T. That would be the case when the expression was that of sum of quantities. Here I would write delta G mod, that is the magnitude of the error, delta G upon G, is equal to delta H upon H plus 2 times delta T upon T. This 2, which multiplies the error or uncertainty in time, comes because of the power t square in the expression on the right hand side. Let's see how we can get at this expression. Though you can take it as a rule, you may be interested to know how did we come to this rule. Once more we begin. G is 2h upon t square. Now there is an error in G that we call as delta G. We denote by delta G. So G plus minus delta G. And what is this error due to? It is due to an error in the height measurement and an error in the time measurement. So on the right hand side, instead of h, I write h plus minus delta h. And for time, I write t plus minus delta t. So I take out the large quantity G common outside in the next step. I take out 2h upon t square common on the right hand side expression. In fact, these things cancel out. And what I am left with is the last expression on this page. Continuing, we can apply an expansion of this series 1 plus x raised to power n, noting that x is small. Here x is the quantity delta h upon h, and we are assuming that the error in h is much less than the value of h. Similarly, the error in time is much less than the value of the quantity t. We can do an expansion of the series, and this is the binomial expansion, and we retain terms only up to first order in error. That is, when delta h and delta t get multiplied, because both of them are small, imagine one is 0.01, the other quantity is 0.01. If you multiply them, that product would be very, very small. So we can neglect terms which are of the order of delta square. So we are left with only 3 terms. We can cancel out 1 from the left hand side and the right hand side. And here we have the expression that I mentioned to you, the rule for product, the propagation of errors when product of quantities is involved. Let's substitute the values that we have for our problem. Delta G upon G then becomes 0.1 upon 10 plus 2 times 0.1 upon 1.4. I can multiply them and I can get an answer which looks like 1.559. I don't have to report to so many significant digits. I can simply write this as 1.6 meter per second square. This is the error in the acceleration due to gravity as inferred from the experiment, and the value of G from this experiment is 10.2 plus minus 1.6 meter per second square, mostly because our stop clock has a very poor accuracy and the time of fall was very short. Yet the actual value lies within the error bar. There is another problem from a different area of physics, from the topic of rotational dynamics. A solid sphere is rotating about an axis passing through its center. The values of its mass, radius, and angular speed are: m is 25 kg plus minus 0.1 kg, r is 10 plus minus 0.1 centimeter, and the angular speed omega is 10 plus minus 0.1 radians per second. The question says, what is the error in the estimate of its angular momentum, the magnitude of the angular momentum? So here we have the sphere, and any axis passing through its center is a principal axis. Along the principal axis, the vector relation L equal to I omega holds. We are not interested in the vector aspect here. We are only looking at the magnitude. So the magnitude of L is equal to I times the magnitude of the angular velocity. For a solid sphere, the moment of inertia I is given by 2 by 5 mr square, where r is the radius of the solid sphere. From that, we obtain that the angular momentum L is 2 by 5 mr square omega. We can use this expression now and note that the quantities m, r square and omega appear as products. You can also think of it as m times r times omega. So using the product of errors, how the propagation of errors for a product of quantities, we can write delta L upon L for the left hand side is equal to delta M upon M plus 2 times delta R upon R, and further you can add delta omega by omega. We don't worry about the constant quantity multiplying the whole thing, that is 2 by 5, because there is no error involved in a constant quantity. I have already discussed the derivation of this result in the previous problem, so let us assume this is true. You can take it to be a rule and we proceed. We can plug in the values, and here we have delta L upon L as 3.4%. What is L itself? Or we can call it L best, our best estimate based on the average values of M, average values of R, and average value of omega. If you plug that in, you get 1 kg meter square per second as the best estimate, and the error is 3.4% of that. So one would report L to be 1 plus minus 0.034 kg meter square per second. Let's move on to the next problem. This is from a completely different domain. Imagine you are performing experiments on the moon. Several rockets have been launched from the surface of the moon. In fact, rockets have actually been launched from the surface of the moon. One of them brought Neil Armstrong back to the Earth. Rockets were launched from the surface of the moon and they were given an escape velocity. The statistical error, when you launched many rockets, you can find out the escape velocity in each launch, and then you can take the average, and then you can find the standard deviation, and you can report the statistical error in the magnitude of the escape velocity. The question says the escape velocity is 2.38 plus minus 0.05 kilometers per second. Astronomers who were observing the moon from the Earth, they also found that the moon was slightly flat at the poles. The Earth is also slightly flat at the poles, and the moon is also slightly flat. Probably there is the common aspect of rotation about an axis, which both the Earth and moon do, and that is responsible for this flattening at the poles. So what did they find? They found that the radius is not one single value. The radius is 1737 plus minus 1 kilometer. The question says what is the mass of the moon and the uncertainty or error in the estimate. First, let's do the simple job of finding the mass of the moon. We have a picture I have sketched here of a rocket leaving the surface of the moon with an escape velocity that is given by under root 2 capital G times m, the mass of moon, divided by r, which is the radius of the moon. Using this, we can find the mass of the moon, and for that we will need to plug in the gravitational constant capital G, that is 6.67 into 10 minus 11 in SI units, meter cube per kg per second square. If you plug that in, what you get is the mass of the moon to be 7.37 into 10 raised to 22 kilograms. Find what is the error. This is an experimentally derived quantity. We would like to know how sure we are about this value. Let us look at the expression for the escape velocity, which is under root of 2 times the gravitational constant times the mass divided by the radius. We can use this expression and the rule for the propagation of errors for a product of quantities to write the first expression. On the other hand, it would be more useful to bring the mass on one side, so I have brought the mass on the left hand side and equated it to v square r upon 2g. From this, we use the propagation of errors to write delta m upon m is equal to 2 times delta v upon v plus delta r upon r. We can plug in the values, and the dominant uncertainty comes from the escape velocity, the error in the escape velocity. Plugging the values, we get the uncertainty in the mass of the moon to be 0.29 times 10 to the 22 kilograms. Here I have neglected the uncertainty involved with the gravitational constant. In fact, the gravitational constant, as experimentally measured, also has a very tiny uncertainty, and that can be neglected in comparison to the experimental uncertainties in this problem on the escape velocity and the radius of the moon. Here is a fifth problem. Well, this kind of problem you commonly encounter in planetary motion, but I have kept the values of masses very small, not realistic about how planets' masses are. This is just to keep the solution very simple. A system of two interacting bodies in free space is described by a reduced mass. I'm not sure if you have learnt about reduced mass, but even if you have not learnt about it, you can take this expression. There is a quantity called reduced mass mu, which is given by m1 into m2 upon m1 plus m2. If m1 is 2 plus minus 0.01 kg, m2 is 3 plus minus 0.02 kg, we know the uncertainties in the respective masses. The question says, what is the uncertainty in the reduced mass? Let's look at the solution of this problem. Before I proceed, I would say that though I have chosen the values 2 kg and 3 kg to make the solution simple, or the numerical calculation simple, in practice, this could represent the motion of two planetary objects in space, and what immediately struck me was Pluto and its satellite. Pluto, which until yesterday used to be a planet, and it has a satellite, and their masses are quite comparable, and Pluto and its satellite go around each other. And when they do that, to describe their motion, you need to have this quantity called reduced mass. Of course, the masses would be 10 to the 22 times more than what I have taken. Let's return to our problem with the 2 kg and 3 kg masses in free space going around each other. Mu is 2 into 3 upon 2 plus 3, which is 6 upon 5 kg, or the reduced mass is 1.2 kg. If you look at the expression for mu, you can note that 1 upon mu is 1 upon m1 plus 1 upon m2. Now this looks like sum of two quantities, but then they are in the inverse. This is 1 upon mu. It's not mu is equal to m1 plus m2. It's 1 upon mu is equal to 1 upon m1 plus 1 upon m2. How would we write the propagation of errors when we have an expression of this kind? When you have no simple rule in your mind to solve the problem, you can always resort to first principle, that is, write on the left hand side 1 upon mu plus minus delta mu. This delta mu is the error in mu. It arises because of the right hand side, and the right hand side has errors 1 upon m1 plus minus delta m1 plus 1 upon m2 plus minus delta m2. We are now going to relate the delta mu on the left hand side with the uncertainty in the masses on the right hand side. We can proceed by taking mu common, so that we have an expression of the type 1 plus x X is a small quantity. It could be delta mu upon mu, delta m upon m. Either way, it's a small quantity. One can use an expansion of 1 plus x raised to minus 1, a binomial expansion, where x is small. So when you do this expansion and you cancel out the terms, you are left with only delta mu upon mu square is equal to delta m1 upon m1 square plus delta m2 upon m2 square. Summarize, this is the expression I have got for the error in the reduced mass. It is m2 square delta m1 upon m1 plus m2 the whole square plus m1 square delta m2 upon m1 plus m2 whole square. I call this expression as starred expression. We can also derive this same expression from a different and more elegant route, provided you know calculus. If you do not know calculus, don't worry about it. We have already derived it from a different method without using calculus. But in case you know a little bit of slightly advanced calculus, functions of two variables, then I would like to show you that it's simpler to arrive at the expression star. Let me come to this expression. Delta mu is function of two variables, and you can write delta mu as dou mu by dou m1 into delta m1 plus dou mu by dou m2 into delta m2. Dou is different from the derivative d. When we are writing dou m1 of mu, what I mean is m2 is kept constant. Mu is a function of two quantities, two parameters, m1 and m2. If you keep one of them constant and vary the other, how does mu change? Dou mu by dou m1. This is the chain rule for function of two variables when you try to find the change in the quantity which is a function of two variables. Looking at the expression for mu, I can take the derivative with m1 and write the first term. I can take the derivative with m2 and write the second term. In each case, the first case I will keep m2 constant. In the second case, I will keep m1 constant. And in a couple of steps, I have the same answer as star. Now that we have the expression for uncertainty in the reduced mass, we can plug in the values of m1, m2, delta m1 and delta m2. Having done that, we can obtain delta mu, which I have done here on this slide, and delta mu turns out to be 0.007 in kilograms, and a mu is 1.2 plus minus 0.007 kilograms. This next problem is about IV characteristics for a PN junction. This is a topic you will likely encounter in the NCERT textbook of class 12th in the second part. But we are not here to discuss the origin of this expression or what is a PN junction. Given this expression, if you perform a measurement with certain uncertainties, how would these uncertainties or errors propagate? So the question says the IV characteristics for a PN junction in forward bias is given by I, which is the current, is equal to I naught exponential or e raised to power E capital V upon kBt minus 1. Let me explain all the quantities involved here. As I mentioned, I on the left hand side, capital I stands for the current passing in the PN junction. I naught is a constant quantity having dimensions of current, which makes the expressions on left hand side and right hand side dimensionally consistent. The quantity in the exponential is E. E is the charge of an electron. Capital V is the bias, the voltage bias you have applied to flow the current through the PN junction. Kb is the Boltzmann constant, and capital T is the temperature, the absolute temperature in Kelvin. Firstly, you can notice that when the voltage is 0, the current is 0. So this is something we would expect for the PN junction. When you are not applying any bias, no current should flow. On the other hand, when you apply the bias, the current increases very rapidly. Now consider what the question says: two measurements which were performed by applying voltages V1 as 52 millivolts with an error of 1 millivolt and V2 26 millivolts with an error of 1 millivolt. We've applied these two different voltages, and because of the error or uncertainty or the resolution in the voltage application, there is a certain error in the current which is measured. To simplify the problem, I have chosen the value of the voltages to be 52 and 26, and the reason is given in the hint here, that KBT, Kb being the Boltzmann constant, T being the absolute temperature, their product has dimensions of energy, and its value, when you take the Boltzmann constant, multiply it with 300 Kelvin and divide it by 1.6 into 10 to the minus 19 to convert joules to electron volts, you will get the value as 26 milli electron volts. 26 into 10 raised to minus 3 electron volts at 300 Kelvin. So that is a hint given. Let's proceed with the solution. Let's look at the expression again. I is given by I naught exponential EV by KBT minus 1. To proceed, I can take the derivative of both sides, and which pulls out a certain quantity E upon KBT from the exponential. And rearranging the terms, I can write delta I in terms of delta V. Delta I depends on delta V. It also depends on the value of V. So if I look at the ratio of the uncertainty or the error in the current, which is delta I1 upon delta I2, it will be given by exponential e raised to EV1 minus EV2 upon KBT into delta V1 upon delta V2. That's the last expression on this slide. And plugging in the values, I get this very simple result that the uncertainty in the current at measurement 1 is E times the uncertainty in the current in measurement 2. If you plot the IV characteristics of the PN junction in forward bias, they would approximately look like this. And our result says that the measurement in 1 will have a wider uncertainty, though I have not depicted that. I have simply shown a crossbar to say that there are certain uncertainties in the voltage, and correspondingly there are certain uncertainties in the current. But where the slope is steeper, the curve has a steeper slope at the higher voltage, there the uncertainty in the current due to the same uncertainty in the voltage is higher. Therefore, the uncertainty for delta 1 is more, and in this particular case where the values were given, we found that delta I1 is E times delta I2. So let's look at the next problem, which is from the topic of dual nature of radiation and matter, and you would find this in the NCERT textbook of class 12th, part 2. The question is about photoelectric effect. You may remember photoelectric effect was discovered by Einstein, and it is a direct evidence of the quantum nature or the discrete nature of electromagnetic radiation. Some indirect evidences were already there from Planck's ad hoc explanation of the black body radiation, but it was the photoelectric effect which provided the direct explanation of the quantum nature of electromagnetic radiation. So in this question, we have a wavelength of electromagnetic radiation which is incident on a metal, and the wavelength is 450 nanometer. Now, what can this electromagnetic radiation do? It can excite an electron in the metal and it can provide it energy. But before it can take the energy, the electron also has to overcome what is called as the work function. Once it overcomes the work function, it is free to propagate like a free electron in vacuum. The question says the photocurrent is brought to zero by applying an external stopping voltage of 0.6 volts. If the wavelength is measured with an accuracy of 1 nanometer, so we are not sure whether we applied 450, maybe it was 449, maybe it was 451. And the uncertainty in the stopping potential is 10 millivolt. Again, you are using a device to stop by applying a certain voltage, and this device would have some resolution. You cannot arbitrarily apply 0.6000 so on. There will be a certain resolution where you have to limit yourself, and we call this the uncertainty in the voltage. So that is 10 millivolt. Find the value and the uncertainty of the work function in electron volts. Let us look at the solution of this problem. Here is a schematic. You have electromagnetic radiation which is incident, h nu, and the electron overcomes the work function which is phi naught, and then it leaves with a kinetic energy k, but you can apply a voltage to stop these electrons, and that voltage is V naught. So from conservation of energy, you would write E times V naught is h nu minus phi naught. Or rearranging the terms for the work function, phi naught is hc by lambda minus ev naught, where I have written the dispersion relation lambda into mu is equal to c, which is the dispersion relation for electromagnetic radiation. Our first job is to find phi naught before we find the error in phi naught. So plugging in the quantities, the Planck's constant, the speed of light, and the wavelength given to us, hc by lambda is 2.75 electron volts. In fact, if you multiply them as given here, you would get the answer in joules, but then you can divide by 1.6 times 10 minus 19 coulomb, which is the charge of an electron, and you can write your answer in the energy units which are called as electron volts. So 2.75 electron volts. Phi naught is of course the difference of two quantities, 2.75 minus the stopping potential times the charge of the electron. So then we get phi naught is 2.15 electron volts. This work function actually corresponds to a metal, that is cadmium. But the interesting thing we wanted to look into in this problem is the propagation of error. Suppose I know the wavelength with a certain uncertainty. Suppose I know the voltage, the stopping voltage with a certain uncertainty. What is the uncertainty in the work function that I have estimated? One can write the following expression. Delta phi naught is hc by lambda square into delta lambda plus E times delta V naught. Let's see how we arrived at this expression. Phi naught is h nu by h nu minus ev naught. If we write it in terms of the frequency rather than in terms of wavelength, here we can directly apply the error as a propagation of error for sum or difference of quantities, because clearly there is a sum difference involved here, but we will still take the positive sign. As I've mentioned before, the error could be plus or minus, and when we look at the worst case scenario where the errors add up, you will write h nu delta nu plus E times delta V naught. So what about delta nu? Now we need to go from the uncertainty in the frequency to the uncertainty in the wavelength, because what we are provided is the wavelength and its uncertainty. Here we make use of the dispersion relation for light. C is lambda times nu, and we can take the derivative of nu, the frequency, with the wavelength lambda, and what you get is minus C by lambda square, or delta nu is minus C times delta lambda upon lambda square. In the last expression on this slide, I have connected the uncertainty in the frequency to the uncertainty in the wavelength. And I will plug this in onto the second expression given in this slide. And what do I get? Delta phi naught is hc by lambda square into delta lambda plus E times delta V naught. You will note once again that I have dropped the negative sign because delta lambda can be positive or negative. After all, it's 450 plus minus 1 nanometer. So we just work with the magnitudes or the absolute values of the errors. There are two terms on the right hand side. Let's evaluate the first term. We will plug in the Planck's constant and the speed of light and divide by the wavelength square, taking care of all the units to be in the SI units or any other consistent unit system. And I get the value as 9.8 into 10 raised to minus 22 joules. This I can divide by 1.6 times 10 minus 19 to write my energy in terms of electron volts. And this gives me the work function keeping to only 1 decimal, 6.1 milli electron volts. What do we get from term 2? The uncertainty in term 2 is related to the error or the uncertainty in the stopping voltage, and this is clearly found to be 10 milli electron volts. The total uncertainty in the work function then becomes 6 plus 10 or 16 milli electron volts, and we can report the value of the work function plus minus its error as 2.150 plus minus 0.016 electron volts. Let us look at the next problem, which is from a very different area of physics. This is optics. Light is incident at the air-water interface at an angle I measured from the normal to the interface. It is refracted at an angle R. Let n be the refractive index of water. If the incident and refracted angles are measured with an error delta phi radians, find the angle I where the error in the refractive index is the maximum. So let us look at this diagram. The light is incident at the air-water interface and it makes an angle I with the normal to the interface. It is refracted, it bends closer to the normal, and the angle of refraction is R. And these angles are related by the Snell's law, which says sine of the incident angle upon sine of the refracted angle is equal to the refractive index of water divided by the refractive index of air. Refractive index of air being almost 1, I can write this equal to n, where n is the refractive index of water. So we have the expression we are going to work with. Sine I upon sine R is equal to n. So here n is sine I upon sine R, and we are required to find the uncertainty in the refractive index n, which I denote as delta n, due to the uncertainty in the angles I delta I and the refracted angle R delta R. this question appears a little more complicated than the questions we have encountered before. Though it looks like we have division of two quantities and we can use the rule, the common rule for the propagation of errors of product or division of quantities, yet there is the sign function which is there and which adds to the complexity of the question. How would I solve this? Let me write the first expression, which says delta n upon n. The left hand side is delta of sine I upon sine I plus delta of sine R upon sine R. Why do I write this? Let's define sine I to be f, sine R to be g. F and g are two quantities. Then n is simply given by f upon g. Now you can solve this by treating it by the product or division rule for the propagation of errors, and you will write delta n upon n is delta f upon f plus delta g upon g. We can plug in what is f and g, so we have delta sine I appearing and delta sine R appearing. Now they need to be given meanings. Delta sine I is the error in the quantity sine I when there is an error delta I in the angle I. Here I write the result, delta sine I is equal to cos I times delta I, and similarly for the refracted angle. The basis for writing this expression is the fact that the derivative of sine is cosine. So d sine theta is cos theta d theta, and that's what I've used to write the expressions given on the top. We can plug this in to the last expression on the previous page, and then we have delta n upon n is cos I delta I upon sine I plus cos R delta R upon sine R. So indeed we have related the uncertainty in the angles with the uncertainty in the refractive index. I call this expression star. Now there is an alternate way. If you do not wish to use any calculus, you can start by writing the original expression, that is Snell's law, and Snell's law says n is equal to sine I upon sine R. I can write n plus minus delta n. The delta n is the error in the refractive index due to the error in the measurement of the incident and the refracted angles. So is equal to sine of I plus minus delta I upon sine of R plus minus delta R. In principle, I can proceed in this direction, but it looks a little more complicated to handle functions of this type. Rather, I will proceed with the second step, where I had written sine I to be f and sine R to be g, and then I had arrived at delta n upon n is equal to delta sine I upon sine I plus delta sine R upon sine R. But I will solve this without using any calculus. So you can always do the following. To find delta sine I, you can take sine I plus delta I minus sine I divided by sine I. We are dividing it because we have delta sine I upon sine I. So the denominator here is from the previous expression. Now you can expand sine A plus B as sine A cos B plus cos A sine B, and cancelling all the terms, we have cos I upon sine I into delta I. In this, I have taken sine of delta I to be delta I and cos of delta I to be 1, because delta I is a very small quantity. So it follows that delta n upon n will be cos I delta I upon sine I plus cos R delta R upon sine R, which is the same as the expression star that we derived before. Now noting that the uncertainties in the incident angle and the refracted angle are both the same and both are equal to delta phi, I can write the uncertainty in the refractive index delta n to be equal to n times cot I cotangent I plus cotangent r into delta phi. When will this be maximum? Well, actually you should use, to be precise, an advanced approach called Lagrange's method of undetermined multiplier, where we are trying to maximize this function of two variables being I and R, where the two variables are related to each other. That is, there is a constraint. The constraint is the Snell's law. I will not go through that advanced approach. I just made a mention of it. What you can notice is for cotangent I and cotangent R, they will be maximum when the values of I and R are very small, because the denominator would simply blow up. In that case, we will have, say, sine of I becoming I in the denominator, causing the 1 upon denominator to blow up. And so the maximum value of the uncertainty in the refractive index would happen at the grazing angles when I and also consequently R are much less than 1. Let's look at this next problem, which deals with dimensions of physical quantities and what can be derived from that. Here I am introducing a new quantity, which is a vector S given by the cross product of electric and magnetic fields divided by mu naught. You may not have heard about this quantity. You may or may not have heard about it. It is called the Poynting vector, spelled as Poynting, Poynting vector. Even if you have not heard about it, don't worry. In this question, I assume that the student has not heard about it. So what does the question say? The question says a student overheard a conversation where this conversation was happening in an advanced classroom where a new quantity was being defined. This quantity he heard was S. The vector S is E cross B upon mu naught, where E is the electric field, B is the magnetic field, and mu naught is the permeability. The student also heard that this quantity had some relation to the intensity of electromagnetic radiation. As you know, the electromagnetic radiation is associated with an electric field and with a magnetic field, which are transverse to each other and also transverse to the direction of propagation. Therefore, E cross B will not be 0. In fact, E cross B will be along the direction of propagation. Use dimensional analysis, the question says, to help the student identify what this quantity S is. It has some relation to intensity. He did not hear it completely, and we have to solve by using dimensional analysis and find out what this S could perhaps stand for. Let's proceed. S is E cross B by mu naught. The dimensions of the electric field are volts per meter. But here we would like to use a different kind of dimensions. As you know, the force on electric charge is Q times electric field. And if we use this expression, noting that force is in newtons and charge is in coulombs, the dimension of the electric field are Newton per coulomb. It's equivalent to volt per meter. What about magnetic field? Magnetic field has the dimensions in Tesla. Again, we don't want to compare Tesla with Newton and Coulomb. We have to bring all the quantities on some common dimensions. So it may be helpful if we use Lorentz force expression. Lorentz force gives the deflection of a charged moving particle under a magnetic field, and that is F is equal to Q times V cross B. V is the velocity of the particle. From this, the left hand side, the force is in newtons. The right hand side, Q has dimensions of coulomb. velocity has dimensions of meters per second, and we can write the dimensions of magnetic field in terms of newtons into second upon coulomb into meter, or Newton upon ampere into meter, because coulomb per second is amperes. So here we have written the electric field and the magnetic field in terms of some common dimensional quantities, and we have to use dimensional analysis to find what S may stand for. But there is one more quantity, that is mu naught, the permeability. Permeability is a constant. As you may remember, it is 4 pi times 10 raised to minus 7 henries per meter. That is the SI units. And we also say, instead of henries per meter, we can say Newton per ampere square. Let's see, if you do not know about the units of permeability, can you quickly derive it? So you may remember this expression for the magnetic field. B is mu naught into H plus M. This is what we write for magnetic field and magnetization inside a material rather than in vacuum. This can be used to find the dimensions of the permeability. Noting that magnetization is a dipole moment per unit volume, delta M upon delta V. And what is dipole moment? It is current into an area. If you imagine the dipole moment to arise from the flow of a current loop. From this we can write mu naught as the dimensions of mu naught as the dimensions of the B, the magnetic field B, divided by the dimensions of the magnetization M. So we have already found in the previous slide that the dimensions of magnetic field are Newton upon ampere into meter, and we divide it by the dimensions of the dipole moment, which is ampere meter square, and the volume, which is meter cube. Cancelling out the terms, we get the dimensions of mu naught as Newton per ampere square, which is expression 3 on this page. Using 1, 2 and 3, where we found the dimensions of the quantities electric field, magnetic field, and permeability. So we had electric field into magnetic field, rather cross product, divided by the permeability. So what would be the dimensions of this new quantity S? The dimensions of the electric field into the dimensions of the magnetic field divided by the dimensions of permeability. A lot of terms cancel out and you are left with Newton per meter into second. I can multiply both the numerator and denominator by meter, and Newton into meter is joule. So this is joule per meter square into second. And joule per second is intensity, so it is watts per meter square. The student already heard that it is some kind of an intensity of electromagnetic wave, and from this dimensional analysis you can see that S has dimensions of intensity per unit area because it's divided by meter square. So you can see that dimensional analysis can give us some insight on what the quantity may represent. Here it represents intensity per unit area, and when you dig deeper, it's actually the intensity per unit area crossing an area which is normal to the direction of the propagation of electromagnetic wave. Here is the last question for the class today. We go back to the propagation of errors, and in this problem I have chosen from radioactivity. In a radioactive material there are 3000 particles initially, and in this material the radioactivity is very rapid, so it decays very rapidly. Typically you have radioactivity over a period of say 1 year, but here I have chosen a very small time. In 10 seconds 1000 plus minus 40 of them are found to have decayed. What do you mean plus minus 40? Either 1000 have decayed or 1040 have decayed or 960 have decayed. How can we assign error bars? This could be statistical error bars. Maybe you repeat the experiment separately a number of times and you get an average value of 1000 have decayed after 10 seconds and there is a standard deviation error of 40. So 1000 plus minus 40. Now, if the resolution of the time, because you are measuring that after 10 seconds, so many have decayed, but how accurately do you know the time? So if the uncertainty in the time is 0.1 second, then find the uncertainty in the rate constant. So we are given 3 hints here. One is the law for radioactivity, which is given by an exponential decay e raised to power minus lambda times t. Capital N on the left hand side is the number of particles at time t, and N naught is the number of particles at time t equal to 0. We are also given the ln of 3 by 2, and we are also given that the expansion of ln of 1 plus x, where x is a small quantity, is given by simply by x. Let's proceed to solve this problem. We'll first find the decay constant and then find the uncertainty in the decay constant. Now, n of t is 2000 after 10 seconds, because 1000 of them have already decayed, so you are left with 2000, and 2000 therefore is equal to n naught, which is 3000, into e raised to power minus lambda into the time, which is 10 seconds. So solving this, we get lambda as 0.0405, second inverse. Now the question says, what is the uncertainty in the decay constant? Let's look at the next slide. This is the expression for radioactivity, and we can take the ln of both sides to write ln of capital N is ln of n naught minus lambda t. We need to find the uncertainty on the left hand side and relate it to the uncertainty on the right hand side. And here we go. Delta of ln n is minus delta of lambda into t. So what's the meaning of delta of ln n? It means take ln of n plus delta n, that is the value of n plus the error delta n minus the original value, and that with using the rule for ln gives me ln of 1 plus delta n upon n. Whereas on the right hand side I have minus delta lambda into time minus delta t into lambda. Now we can use the expansion of ln of 1 plus x, where x is a small quantity, to simply write it as equal to x. So we had ln of 1 plus delta n upon n on the left side and in the last slide, and that becomes simply delta n upon n, where n is the number of particles at time t. That is equal to, now we are looking at errors, so the magnitude of error in the decay constant delta lambda into time plus the error in the time measurement into the decay constant. You can of course rearrange, but take care of the sign that we are looking at the worst case scenario, so you have to actually add the error in delta n with the error involved in the time measurement. So if you plug in the quantities, we know that in 10 seconds 2000 particles are there. We know the uncertainty in the time delta t, and we also know delta n. Plugging all these values, we get the error in the decay constant to be 0.024 second inverse. So that is the end of this lecture, and it was my pleasure solving these problems for you, and thank you for your attention. Bye.